Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
My name is Andy Bagel. I'm a researcher in the HIP research group, Human Interactions and Programming. And I'd like to introduce Beth Simon, who is a faculty member at University of California, San Diego. And it's actually funny, she's a faculty member, but she has a very interesting title alluded to in her talk outline, which is Lecture with Potential Security of Employment. And there's a lot of history that goes into that kind of title, certainly from professors who are very protective of the word tenure. So in any case, Beth is going to, she's got a long history in doing a lot of educational work with kids learning to, with college students learning to program, and she has also worked on something called Classroom Presenter, which is actually being used to present her talk today, which is kind of a merge of PowerPoint and tablet PC, so she's going to be drawing on her slides today. And today she's going to be talking to us about studies of programmers and how they can be used to inform training, instruction, and practice. So,
thanks, Andy. Thanks, everyone. Thanks for showing up in the coveted after lunch time slot. But don't worry, I'm used to teaching at this time, so we'll try to do some things to not only portray how much I'm interested in the subject that we're talking about, but maybe even get you to give me your opinion on that we might be able to utilize in doing this sort of work. So I'm going to be talking about some studies of programmers, and particularly I'll be coming at this right now from the educator point of view. That is, I'll be presenting some work that's been done recently amongst a number of higher educators around the world. And our real interest as educators and also as researchers is trying to improve instruction and training in computing, computer science, those areas. And as stated here, we see a lot of that. Not only on the part of those people trying to learn computing topics, but on the part of those people trying to teach them. And this is really what we'd want to see. We're not really out there to torture them. We'd like to have happy programmers. And so we're interested in trying to see how to make this transition take place. So I'd like to start off with a brief definition of the problem. It is hard to teach computing, programming, and software development skills. And I'm guessing that a number of you not only agree with that statement, but maybe even have some rationale about why you think it's difficult. So I wanted to start with an open question that we could maybe discuss for a minute or two. Why do we think teaching programming and computing is difficult? From your own experience or from observing others, anybody have anything they want to throw out there about why they think it's difficult? Yeah.
Huge class sizes.
Okay, so maybe if we're talking about the formal learning environment in higher education, we might have huge class sizes, possibility. I've also taught a beginning program class of size 3, and I can't tell you I don't think it was any easier than teaching 140, just different. Anybody else have any memories? Yeah.
From my experience, I just remember that you're learning concepts at the same time as syntax and language grammar and that kind of thing. And so it's frustrating trying to put into practice what you learn when you don't necessarily have all the syntax rules down.
Yeah, definitely. The fact that this is a professional practice. It's got both theory, concepts, and practice that we at least teach together, usually. Yeah.
There's a really wide variety in how easily people get it. So
okay.
You have a non-homogeneous class, which is a typical case.
So there's sort of a wide variety, often not only of prior experience, which can be one thing, but even if you try to get people of the same experience level into class, some people seem to get it faster than others. I don't quite even know how to phrase that, but it's just speed or ease of acquisition.
I think it has to do with the styles of learning as well.
Okay, right. So might have to do with styles of learning, etc.
In my teaching experience, I also found that a lot of people don't have the background or the the skills in logical, rigorous thinking.
Yeah. Anybody know that in the United States there is no required course anywhere in the K through 12 called logic? You can graduate with a high school degree and not ever have been officially taught logic or logical thinking. And in fact, even at the higher education level, a lot of students never take a discrete mathematics sort of course where we tend to go over issues of logic. And it almost boggles the mind sometimes. Yeah, so I think all of these are in fact issues that we've seen in programming. Yeah.
Another thing is to it's all ties in together, but sustaining interest.
Yeah. Sustaining interest, boy. I can really go there. I was banging my head against the wall 3 weeks ago as I realized I'd done nothing but work with them for 2 weeks on the difference between passing a parameter that's a reference object versus, a primitive type. And I'm like, why? Why in the first 10 weeks of instruction am I spending 10 weeks on this? Why aren't we solving cool problems?
I think there's cultural issues too. Like, the computer people are dorks and poets are cool, and so I want to take a poetry class and not a programming class.
Yeah, that probably has a lot to do with who we get into our classrooms, but you haven't even given me a chance to scare them away yet there, and yet we're going to get there. Yeah?
Sometimes there's a difference between people who are so used to just being passive about things, whereas in the computer course, you have to actively get in and try things.
Yeah, I mean, certainly one of the things you hear educators, well, if they would just play with the code, right? If they would just log on the machine and play around with some code. On the other hand, the grand majority of educators don't do that in the classroom either, so how would the students know to model that, or what even to model in doing that? And we don't do it for them, and we certainly don't show them the process by which we learn things, maybe. All right, cool, awesome. Well, thanks for the input, guys. I do want to ask you one very simple question, and if we had wonderful internet access, you could all vote with your laptops. And anyway, but we'll just do a quick show of hands, or maybe a quick discuss with your neighbor for 10 seconds, and then we'll try to see what our consensus is. So one of the ways we could drill down on that very large problem of it's very difficult to teach programming is to ask ourselves, first off, what's the average completion rate of a first programming course in higher education? Is it A, 90%, B, 80%, C, 60%, D, 50%, or E, 40%? So I'll give you guys 10 seconds to discuss with your neighbor and try to come up with an answer, and then I'll let you know what it is.
That includes the first 2 weeks of the massive dropout.
Oh, you can define it. Well, so there isn't. Okay, who thinks they know what the right answer is? Not sure. In fact, not sure is the right answer. We don't know. There's currently a survey that's gone out to the listserv of computer science educators around the world asking people to please fill in this form and tell us for your institution, for as many years as you can give us, this information. I am the beginning computing instructor at a very large state institution of somewhat high repute, and I can't get this data. Partially because we don't know how to measure this. I mean, this survey has actually gone into detail. They want to know, how many people originally enrolled, how many people were still there after week 1, how many people made it to the final, how many people took the final, how many people passed, what's your definition of pass, because this is a worldwide effort. It's really hard to define. But we haven't tried. I mean, and this is an issue. The abstract of this talk says, we've had 40 mumble years of computing instruction because computers appeared 40 mumble-ish years ago. And I like to think that we're now realizing we could spend a little more time rather than saying, oh, wow, these machines exist. We need to train somebody to program them. We could start to actually critically think about how we're teaching computing. And we can start with very simple things about how effective are we being? How do we want to measure this? Let's set up some guidelines, etc. So what I'd like to talk to you about today is to give you a little bit of overview of some recent very interesting work that's gone on in studies of novice programmers. And this has come about because there have been a number of CS educators who've gotten together and been like, look, we're really tired of hearing about these papers that say, well, at my institution, this, or at my institution, that, or I seem to see this. And they got together and they did some multi-institutional studies, and some interesting things came out specifically about novice programmers. We like to study novice programmers for a number of reasons. One, there's lots of interesting issues that novices have. There's something that you end up finding about a discipline as a whole by studying how people first interact with it. And secondly, novice across Sweden, the United States, various places in the United States were fairly similar, whereas if you start talking about students at the junior level, there's maybe a significant amount of difference in how you teach that would have given them different backgrounds at that point. So I'll talk about 3 seminal studies that have captured the interest of the CS education community in the last couple of years. I'm going to then pull that all down into a brief interlude on my theory about the power of qualitative work and why we need to bring qualitative work specifically to the study of computer science education at this point. And then talk to you briefly about some work in progress that I'm doing with various groups of people and some proposed work I'm hoping to do here at Microsoft. So one of the seminal beginning pieces of literature in recent history, in the past 4 or 5 years, that has almost led the way in terms of describing how we want to study novice programmers as educators, was done originally in what's called an IDISI working group. IDISI is one of the computer science education practitioner conferences. It's particularly the one that happens in Europe every year. There's an American one that's called SIGSI. And IDISI has this function that before the conference there's a 2-day period where you can propose a working group. And you can get a group of people together and study something. And then they guarantee you a publication, so it's kind of nice. Let's see, this was the McCracken Group, and they were in 2001. And this is led by Mike McCracken from Georgia Tech. And they got data from 4 institutions, all in the United States, over 216 students. So hopefully that was some power of numbers here. They asked students to code on a computer a basic calculator program. It was either an RPN calculator, an infix calculator without precedence, or an infix calculator with precedence. And the reason they had to do this variety is they were doing cross-institutional, and different institutions said, I don't think my students would have learned what would be appropriate for that at the end of their first year of study, or this is what would be appropriate for our students. So faculty were deciding at their institution, based on what you've learned in the first year, this is a reasonable programming assignment that we would assume that students who'd passed would be able to do this. Okay, so this work was seminal. It got the ball rolling. They defined novice as a term that we will use in a lot of later work, which is students who are currently taking a course where they would learn how to program a calculator program using stacks or queues. Okay? And this definition of populace has been key in a lot of multi-institutional studies. Now they got these 216 students to do this, got together and over 2 landmark days, evaluated these programs and graded them out of 110 points. They gave 30 points if your code would compile and run with no core dump, so basic execution. You could get up to 60 points for passing various test cases and up to 20 points for validation and style. And at this point, you should all be thinking, so what do I think the average is across 216 students? Take a brief moment. Anybody come up with 22.9?
Oh my God.
Yeah, we're talking way below doesn't compile, okay? Moreover, both the median and the mode were 8. Okay? This is after a year of programming instruction when honestly we really, instructors really thought they can program a calculator, and you would kind of hope so.
You think they'd have already written this code?
Yeah, they might have, in fact. Yeah. They might have had a homework problem, but does that mean, now there's some caveats. I would need to send you the full paper to read about this. They only gave them an hour and a half. We didn't think that was very appropriate. Yes, I know you can do it in 5 minutes, but they did it on a computer, had access to whatever normal environment they use, okay, but still produced something that could not compile. just anecdotally, we tend to observe students, and they don't like do incremental compile. They don't compile every 5 minutes. They're not always in an always deliverable state. They'll just code forever, and then they probably ran out of time. Okay, so that was a very dismaying metric. So they decided they need to look at the data in some other way. So they developed this qualitative analysis called the degree of closeness, where 5 is a touchdown, 4 is close but something is missing, 3 is close but far away, 2 is close but even further away, and 1 is not even close. And even when you try to be a little nicer and be more general there, they had an average of a 2.3. This study, again, 216 people, they did not observe the students in doing this. They did sometimes occasionally sit there, or certain people basically realized that all hell was breaking loose. And so they asked some students afterwards what happened. And you get descriptions of things like, I ran out of time. But there was very little meaning that came out of this other than, oh gosh, we all thought they couldn't program after a year, but gosh, now we really know it. And it was very depressing. So a few years later, after people recovered, another IDISI working group was proposed. This happened in Leeds. We suddenly decided we needed to name them after the location, not after the person who ran it. This was a larger study involving 12 institutions, 7 countries, which was quite nice, 556 students. And we said, well, writing code is very good, but there, in study of English or anything, there's the, can you write something, but there's also can you read something? And code reading is an important skill, we think, although upon reflection we're not sure we teach it. So we gave students 12 multiple choice questions, and that basically asked them to be able to read and trace code with arrays. The great thing about this study is that it included both some cheap data collection, which was 556 students taking a 12-question multiple choice test. Easy there. Some people gave it as part of their final exam. But then there was also rich data collection in that 32 students were asked to do so in a think aloud setting, where they either took the exam or immediately reviewed the exam after taking it and thought aloud while an interviewer would prompt them about what they were doing. And so you get some answers there. They were also encouraged to write on the test, so this was run by an Australian, so they call those writings doodles. And so we have both the answers, we have doodles for 36, and we have transcripts for, I can't remember if it's 32 or 36. What are the questions we're looking at? Just a basic idea. So here's something, again, these are targeted at novices, people who would be in their second semester, say, where they learn stacks and queues. Do this code fragment. We've got an array of Booleans. We have a couple of for loops. The question is, what does the variable count have? So if you can execute code like a computer can, if you can follow the structure, you can answer this. There were also some harder questions, at least they ended up being harder, where maybe there was, I put this on 2 pages because it didn't fit on 1. They would define something. An inversion in an array is this. And they would describe a new concept. And then they would say, here's some skeleton code that's intended to do something. Count the number of inversions in an array. And then there would be something that would be missing. And they say, which of these for loop headers would appropriately complete the code? All right, so the results. Students couldn't write code. Can they read code? They did better. So here's our graph of the results. This is their score. So there were 12 multiple choice questions. You can see the number of students. This is a histogram of the scores received, okay, on those things. Who some of the students didn't answer all 12, so we have a reduced data set here. So students, the overall results are they can read code better than they can write code. It's good. They do better on fixed code, just tracing the code, not on skeleton code where they're asked to fill in. So they are, to some extent, able to play the role of computer, which is an important skill, especially in debugging and things of that nature. On the other hand, students didn't produce hardly any doodles. Okay, they didn't draw anything. And we, in fact, then asked educators to do these same 12 questions. And we found that educators write much more. They make tables and trace values of variables, and they do interesting things with their hands where they keep track of where they're executing in the code. Whereas the students who, we saw very few doodles, and the students who did the think aloud, they didn't really have a coherent description of how they were going through the code. They would make it through sometimes, but it almost seemed miraculous that they got there at the end. And I was particularly involved in a subgroup at that working group where we went through the transcripts and identified strategies that we saw students using in tracing their code, in trying to get to an answer. And we used a grounded theory-based analysis where we just read the transcripts, and then 3 of us discussed, well, I found these words, this looks like a strategy a student was trying to use to get there. And we found 19 different strategies that students collectively used in reading code. Every individual student used a large number of strategies, usually at least 5, more like 10. Okay? And unfortunately, there didn't seem to be any correlation in use of strategy and success, partially because every student used a lot of strategies. But we would see them previewing the code. They'd kind of look at it and be like, oh, there's a for loop. We would see them pattern matching. They would point out, oh, this is a loop over all the indices in an array. I've seen that before. And they would match it to patterns that they were familiar with. We would see them walking through the code, a lot of times unsuccessfully. They would get lost in the middle because they would try to move too fast and abstract away and be unsuccessful at doing that. And they failed in many, many other ways in walkthroughs. They would frequently start over. That was a good strategy. We liked that one. When they would get confused, they would explicitly state they're starting over. And they would pose questions, some of them, which was also a strategy we thought was quite interesting. Why did they switch strategies? Why did they get stuck? We didn't know because, again, even though it was some more qualitatively based data, the way we chose to gather data was just do the think alouds and then come and analyze it later. We didn't really get there and work with them over and over again in a way where we could ask the students questions. And that ended up being, I think, a disappointment that came out from this work. We still didn't get a complete picture of what they were experiencing, even though we were asking them to think aloud. And that ended up being disappointing. All right, a final review study. Can students design code? All right. So a group of about 20 educators from around the world came together. The National Science Foundation funded them to basically learn computer science education research techniques. And they went out over the course of a year and asked students at the same novice level to produce a design for a super alarm clock. And they were given a design brief that described this alarm clock that would be used by college students. And, basically, if you got less than 6 hours of sleep a night for some number of time, an email was sent to your mother, and there was a red alert and a yellow alert and a green alert about all sorts of. So there was a nice little document, 1 page with about 12 bullet points. And then we presented to students with paper, blank paper, and pens and pencils, and said, please produce a design. They were given the following criteria. It should be at least 2 parts and not more than 12 parts. And it should be something that someone else could use to write the code. And I will show you a few screenshots of the variety of things that novice students produce. Here's a nice design. We see some boxes. We've got a database, a controller, an alarm. We have some description of different things, of the controller, of the warning filter, of various things. I don't really know what the right design for this looks like, but this is at least something interesting. Here's another design. A little bit less description, but we have interaction between components. We've got database interacting with other things. We have subparts. We have some organization. So maybe that's an interesting design. This was a very, very, very common style of design, especially amongst novices. We have a main method. All right? That's a very important part of the design. You have to have a main something that you start. You run the clock program, you do something. We have some if statements that are done in English. That's pretty good. And then maybe we have some sort of breaking, chunking up of the thing with set alarm, by alarm, etc. By the way, almost every design was multiple pages. I'm just showing you representative. Also, a lot of stuff that we had. We're seeing comments in here. We're using the commenting structure in C. All sorts of things. We saw a lot of code. And then you'd occasionally see stuff like this. Who knows? But it's kind of an interesting design. Right. So we did not put any, we don't have any numbers like 40% of the designs were right. You don't want to try to assess correctness of design. You just want to see what they think design is. All right. Overview. So what do we really know from all this data? How does this work help us improve instruction or training? Well, we do have some real documented, non-anecdotal, multi-institutional answers documenting success or failure. And that is nice. It's very appealing to the computer science education community. We can show these problems really exist. They're not just problems with my students or my institution or anything like that. These are real problems out there. But what we're really lacking is any real descriptive power or understanding of the problems that students face and how we could improve instruction based on that, okay? So I really believe that at this point in history, in computing education, it's very important that we spend some time doing qualitative research. And we need some very thorough qualitative studies, which could be small, because we've now said that students across the world tend to have similar problems. At least they manifest themselves similarly. But we need some in-depth studies which can give us the important, rich description that we're going to need to get into the process that the students are using in failing or going about whatever it is we're asking them to go about, rather than just giving us the result of what they come up with, where we can ask questions interactively, where we can really try to find out and understand how the student is experiencing some phenomena, how they're experiencing the difficulties they're having in coding, how they're experiencing how they should read a code and why they might want to read code. And I firmly believe that we have to do this, that if we believe in the value of the scientific process, which a lot of us do, that it has some real use in society and in helping us improve something or, you know, well, let's just stick with improve something in a rigorous way, that the first step of the scientific hypothesis is to make observation. And while I stand in front of a large number of students and teach multiple days a week, and you could say that I can make some observations based on that, there's a lot of learning that does not happen in the classroom, especially in computer science where we have conceptual and practical components. And that if we want to understand where the issues are in those learning, we have to observe, and we have to do some rigorous observation. And we can't rely on sociologists or people with PhDs in education to do that, because why would they care about studying computer scientists? Okay, well, maybe the National Science Foundation or somebody would pay them to do so. But we're the ones that know about computing concepts. I mean, how is somebody who has no background in computer science really going to understand the real difficulties students have with indexing arrays? You know, I could work with them a long time on that, but we could do it ourselves. We know what these issues are. So that's my motivation. So just to let you know, now we're going to move along. I want to show you, with that motivation, about 2 pieces of work I have in progress that are both joint projects with groups of about 5-6 people. One is on resources students bring to learning computing, and one is on bug location strategies that novices use in finding bugs. And then briefly talking about some proposed work that I'm hoping to do here in the near future, where we will move a little bit away from the novice higher education student, but to another critical transition period, which is what happens when we shove them out the door and into your world, and they show up for the first time in industry, and what critical skills do they seem to require, and what ones do they perhaps not have, because we didn't teach them. So first, the 2 review studies. I'm very interested in identifying what students can do before we teach them computing. And at a number of institutions across the country, there are separate entry paths into computer science. At my institution, if you answer yes to the following question, do you have any prior compiled programming language experience, then you're placed in one class. If you answer anything else, like what's compiled or whatever, you're put in the class for the people with no prior experience. So we can actually get at this. There's been some interesting work by a fellow named John Hammer in physics, where he's advocating that you have to understand the conceptual background people come in with. People come into their higher education physics class with a lot of experience in the physical movements of things in the real world. But a lot of times those conceptual understandings of how things work in the real world don't mesh exactly with the models that they would be teaching in a beginning physics class. And he says you have to realize, you have to get people to realize, you have to understand what people's real world conceptions are and use those and treat them, tell them when to apply those certain models in the contrived world that they study in beginning physics. And I think we need to do the same thing. our students all have a lot of experience with concepts in computer science. If you ask anyone on the street, if you had a list of 10 numbers and you had to place them in ascending sorted order, they could tell you a way that they could do that. But we didn't actually really know that they could do that, and so we did a study on sorting, where we asked students on the very first day of class to tell us in English sentences how they would arrange a set of 10 numbers in an ascending sorted order. And the good news is they can do it. 69% of students in CS1 courses across there are probably 7 institutions in this study, can describe something that is a correct solution. It reads like an algorithm that we could follow and get to a correct list of sorted numbers. That's good. They can solve problems that are critical to computer science before we teach them any computing. Now we wonder why they don't make it through our classes. But anyway, 57% of them could even describe something that worked in a general case, not just for 10 numbers. Interestingly, the majority of them do not describe comparison of numbers. Pick your favorite sorting algorithm. Selection sort. Find the smallest number, put it first. Insertion sort, merge sort. You're always comparing numbers. Students didn't compare numbers. They didn't say if this number is less than that number or something. They actually described the numbers as strings. So it happened that in the first round we gave it, all the numbers were between the numbers 0 and 999. So they said first you'd put all the 1-digit numbers together, then all the 2-digit numbers together, and all the 3-digit numbers together. And then they told you how to sort within that. And they would say for the 3-digit numbers, first put all the numbers that start with 1 first. If more than one number starts with 1, then you look at the second digit. So they did a form of bucket sort, which is it's sort of kind of like radix sort, which they have a really hard time learning 2 years later. They can never get it, but they do it naturally before we teach them anything. So they don't really see numbers as numbers. Now, obviously, they can switch to do that, and I'll tell you a bit about that in a minute. They also always use the word until rather than while. And this actually validates research that has happened in the past. The students favor post-test loops because it's natural. In the real world, you tend to say, okay, I'll do these sort of things, and then I'll keep doing that until something happens. But you describe what it is you're going to do first. And we saw real variance in use of conditionals or in the focus of their explanation, where they focused on getting a number first, where they focused on breaking it into groups. There was a lot of variance there. So the good results and the bad results of this study. We also performed this study with some non-CS studiers. We wanted to do some additional studies in the future on concurrency and debugging and things of that nature. And we wondered, do we always have to get the beginning programming students right before they start to study? Because that's a really hard time to get them at. They've just come to the university. It's hard to reach them. We thought, boy, if we can study non-studiers of computer science, there's a whole bunch of them on our campus. Unfortunately, after giving this same sorting question to 500 Economics 1 students and then weeding out all the people who claimed they had prior programming experience, we found that they produced statistically significantly different answers in terms of they were much less likely to produce a correct solution, and then a number of other factors as well that I can point you to in the paper. So that was I said that was bad for us as researchers, but it's actually good for us as people interested in computer science. Those people who are self-selecting to study computing are more naturally able to express a correct algorithmic solution to sorting before we teach them. So even though we think they're not doing very well, they're doing better, apparently, than those people who choose not to take our course. Or maybe they would be doing better. All right, now here's the bad. So then we teach them for 10 weeks about Java. We taught them sorting, okay? Particularly, we taught them selection sort because of those students who did produce a numerical type sort, selection was the most common. Unfortunately, after 10 weeks of instruction, we asked them to do the exact same problem, describe in English sentences how they would arrange 10 numbers in ascending sorted order. They're more likely to produce a numerical style sort, almost universally. They use many fewer examples and many fewer words in describing their, so they have become more succinct, which is kind of maybe a good thing. But they're way less likely to produce a correct solution. And in fact, so yes, now we term this Beth Simon considered harmful because I, in fact, taught them, and I taught them sorting, and in the end, they couldn't sort anymore. But what you do see is they've learned a new level of description. Even though you say describe in English sentences, they're trying to give you a more precise answer in terms of arrays and how you'd implement on the computer. And in doing so, they haven't quite connected yet. Okay, they have a very fragile knowledge of their understanding of algorithm to implementation on a computer. But even this needed more qualitative analysis. Yeah, Andy?
Did you ever try to give the students their original answers to see if they understood them as good, or give them other people's answers from week 0 after they've taken the class and see, do you think that this is a proper sorting?
So I didn't ask the question, is this a proper sorting? But I actually selected a student answer that was selection sort and put it up and said, you guys knew algorithms before you got here. And I asked them to read it, and I said, now let's together translate this into some code. And then I realized, upon doing so, luckily I realized in my office, that selection sort from one array into a second array is a lot harder than selection sort in place. But we did, in fact, cover that first. You know, the whole problem, you pick the smallest number and you put it first. Now you've got to mark out that number on the list. And I think that was all a very instructive process for them, because it gets specifically at their differences in conception between real-world manipulation of data and computer manipulation of data. But I didn't particularly get that. That would be kind of fun. Anyway, yes?
I'm just curious how badly what does less likely mean?
Yeah, that's true. I'd need to go look up the exact number. So we went from like a 69 to something significantly below 50. So 40-ish%. But you could see that the thing is, if I'd been there with each of those students and I'd said, no, forget arrays, just tell me, I think they still could have done it. And that's, again, where this was still a quantitative study, in that we just send people out to do it. We need more qualitative analysis. If prompted, could they express a correct solution at a higher level? I got to think the answer would be yes. But that would be much harder to do. I cannot go out and interview, 200 students. Yeah.
This is kind of interesting, because one of the things I think people lack is ways to abstract and think at abstract levels. And what you're telling me is that they were able to do this before.
And we trained it right out of them.
Programming, they can no longer abstract.
Right.
They have to be done in the code. So
yeah.
That seems really bad.
And even more frightening is that I actually require my students to do interviews on every homework assignment where they have to explain code to a TA. So I've actually taught them in some way, or at least I've given them points for being able to explain code. And it's something I'm continuing to work on. I work on more and more every time, because I think it's a very important process. All right, I've got 2 more stages to go and no time. So, bug location strategies of novices. This is a second study that is currently ongoing. We have not collected the data yet, but there's a group of about 8 educators around the world. We meet once a week using voice over IP and talk about what is really important to us, which is students' lack of ability to debug. Because as educators, anecdotally, we believe that debugging or lack of debugging skills is one of those things that is critical to failure in a first CS course and in the first year or 2 of a CS degree. There are some students who seem to be able to do it and some that don't. And in case you didn't know, debugging is not taught in any real curriculum that we know of. Okay, we have now proposed a course, but anyway.
Common problem in interviews where you get people giving them a small programming problem, and a large percentage of them don't even look at their results to see if it is even halfway reasonable.
Mm-hmm. Yeah. Well, I've written it and it compiles, so we're done. That's success by many students. Definition. There's a great paper that basically says my program works, but it won't compile. That's a quote from a student. They have a very different definition of works than we do. Okay, so our study is there are 2 parts. There's actually 3 parts to debugging, but there's 2 parts to debugging that we want to focus on that novices frequently face. First is finding the bug, and second is fixing the bug. About 20 years ago, in fact, exactly 20 years, in 1986, Katz and Anderson had a paper where they claimed that location was the only difficult task for novices. In reading this paper, we don't agree, we being this group of educators who've been reading papers for a year now on novice debugging. And partially it's because they were working in a very specific environment with a restricted section of Lisp and all sorts of things that didn't seem relevant to us today, and we don't think that we will find that. So our goal is we've asked to reproduce the Katz and Anderson study using modern languages. We're not going to restrict ourselves to any one language. We're doing a multi-institutional study. We'll each produce a similar protocol in whatever language and environment of instruction that we use, and try to identify, we're going to have, let's see, do I have details? Oh, I do. Protocol. We will do an observed coding and debugging section. So we'll provide students one of 5 problems. Any multi-institutional study, you have the problem that we all teach differently. So we're using a protocol from from a Perkins paper. You provide people with a set of problems. You let them choose one. You say, pick one that's not too easy and one that's not too hard. And you let them select. They will be given 20 minutes to code. We will, and asked to think aloud while doing so. We will be there and observe any bugging and bug finding that goes on. And then we will, after 20 minutes, we'll stop them and give them a pre-prepared buggy version of that code, which we will be developing using preliminary experiments to determine common bugs that students make in making these, in trying to design these codes. And there'll be similar bugs across all the 5. So that we can try to get things there. And we'll see what they do. We'll give them then 20 minutes to try to debug this code that they've just been working on. And follow that with a semi-structured interview, really trying to now get at the qualitative. When I ask them, we have a set of questions we'll go through and ask them. First just say, so how did it go? And just see if they, oh, it was really hard. Or, well, it was easy. And we're like, oh, really? You didn't do very well. But just to get their perception of what debugging is and whether it's miserable or fun or something. Ask them if they had any strategies that they use. Can they articulate any strategies? We'll certainly utilize our observation and try to come up with strategies that we saw, but do they identify strategies that they use? Ask them how it differs from what they normally do in doing homework, which is their only real, practical component of doing programming. Do they make the same mistakes over and over again? How is debugging your own code different from debugging someone else's code? These are the kinds of things we're interested in that we hope to work with students on. So another interesting study. You could look for a paper on that. Well, we're getting together to discuss the data in June, so in maybe about a year. Last study is a study that I'm very excited that hopefully we'll be able to carry out here at Microsoft and then at a couple other various places in industry, where I'd like to look at a key transition period, which isn't the beginning of learning to programming, but it's sort of what happens once students move out into industry. And so I'm very interested in knowing what software development skills are employed in the first few months of industrial practice. And that may, seem very natural to you guys, but you have to remember, it's always frightening to me as computer science educators, almost universally, none of us have ever worked in industry actually programming, and yet we prepare students in some reasonable way, supposedly, to be prepared to do that. So I'd like to take the chance to come in and really try to observe these sorts of things. I'd like to find out what skills beginning software developers seem to have already comfortably developed and that they're able to deploy those skills to make progress in the first couple of months that they are out working, and what skills do they seem to need to acquire on the job, and how easily do they acquire them. And then my goal from that is to then sort of realize and try to identify if there's any way in higher education, I'm not saying it's going to be easy, that we could potentially teach these missing or underdeveloped skills within the confines of the undergraduate curriculum. So a protocol here might be to still under development, but potentially, again, observe beginning employees in some industry situations using a very ethnographic approach. Follow them around, okay, and just observe them. Don't interfere as much as possible, but do some interviews, and do this sort of at the very beginning and then maybe after a month when they've had a little time to settle in and see what's going on. And then also have them give us some personal reports on how things have gone during that time. So I don't really want to conclude, and hopefully we'll have time to do a nice full discussion here. But I really believe that difficulty in the training of developers or programmers or whatever you want to really call that is an area of critical study. And I'm a firm believer in the scientific process, and I would like to use the process of observation, hypothesis formation, and then experimentation to really draw this area out and do some critical work in it. We have papers that we frequently call Marco Polo papers, which is I went out into the classroom, I saw something, and it didn't look good, so I did this thing and I changed it and they liked it. That's not enough in solving this problem. Okay, we need to start with serious observation, an observation that goes at a detailed level, detailed, descriptive, etc. So those are the ends of the comments that I had prepared. But again, I would like to draw people into a discussion about interests you might have in education, in higher education and training, and then also specifically in industry, and any ideas you might have for the studies that we're still developing. So thank you very much. Yeah.
So when our group does qualitative research among developers here, we don't tend to sweat the observer effect too much. We don't worry about Hawthorne effect, or because the developers we're watching are so motivated by their reputation on their team and how they're going to be evaluated during the annual process. They could care less about us, right? But it seems like with students, if you're going to do qualitative research, you have to be way more careful about the effect of having the professor sit behind you watching what you do.
Yeah.
So can you talk a little bit about that, about how you mitigate that?
Right. It is a serious issue, and it's complicated by the fact that usually the faculty at any given institution who are interested in this type of work are the type of people who are teaching the beginning students, which means they're frequently already in the professorial relationship with students. We try to make sure that in any given time, no one is interviewing students that they're currently teaching. Now, at my institution, even the chances of me teaching somebody else again, not likely to happen. And I actually get a beneficial effect that in my classroom, I teach students the very first term. I talk a lot about my interest in computer science education research, and I make it very clear to them in the whole process of the course that I just want to help them learn better. And therefore, I actually get people who are more likely to volunteer for my studies and to speak with me very frankly, because and this has to also do with other things I do in the classroom where I show them that errors are good and they help us learn, and we discuss them so that they're not as worried about speaking to me. But it is an issue, especially at smaller institutions where you're going to have the same professor over and over again. And we don't have any really good way around that other than students volunteer for studies. It's almost never, certainly in a qualitative study, it would never be a requirement in a class. And we have large human subjects requirements that have all sorts of details about determining when students are in a stressful situation, offering them outs, etc., for making sure that that doesn't go along. But it's difficult. Yeah.
A couple days ago in this very room, we had an expert on testing for sort of these standardized tests at the elementary school level. And I was thinking of just comparing and contrasting where we are. You're talking about how you actually would, sort of observe improvement or something. And maybe I'm thinking about something far more mundane, which is how would you just, do recruiting? How do you do the interview process? How do you figure out, which of these, and in some of these areas, the numbers are huge of the number of candidates applying for positions. And you would think that it ought to, and I think that our interview process is just not terribly effective. We aren't able to, let alone you're talking about how to measure improvement. I'd just like to know how to measure differences. Right?
So do we.
Right. And you would think that at least at the undergraduate level, the numbers are big enough now that it ought to be possible to build a calibrated test that was actually predictive of something.
Well, yeah, we have final exams every term. What is that supposed to be?
Well, we don't know that the final exams are predictive of, a decade of future performance.
Yeah.
All right. That is, let's imagine that what I'm trying to do is to predict the review on some review process in a decade.
Right.
And could I show that that I could develop some test, it could be measurement of anything, that where scores on this correlate either positively or negatively with future performance.
Right. So I think the first thing we have to do is run the study to find out what are the skills that you need.
Well, I don't know that you need to do that in order to do the calibration study.
Well, it's possible, but it would be shooting in the dark multiple times to see if we, and you have to wait 10 years each time.
Well, I understand you have to wait 10 years, but right, the numbers are so large we ought to be able to do it somehow. That is, right now, I don't think we have a clue as to what really matters.
I agree, but I don't think we have any better idea, clue about what matters, or even how to write said test. I mean, let's talk a bit. Have you heard about the physics stuff that was very popular, I think, about a year or so ago? Beginning physics faculty were like, oh, yeah, at Stanford, great, or any school, Colorado, et cetera. We have these great students that get A's on our tests, they're fabulous. Then they gave them a very simple test that said, two cars hit each other, what's going to happen, okay? They can apply these wonderful equations and solve other things, but when you ask a simple test where any physicist goes, well, yeah, if you know this equation and you can apply it, then you would get this answer on this, and the students failed. Senior physics students failed, okay? And this was a real wake-up call to the physics community that we're teaching them to plug and chug, and we think that we're designing questions that therefore you come up with the answer at the end of x equals whatever, and therefore mentally to the students that means this interpretation of physical movement. But physicists recognize that, but students don't. Right, and moreover, they don't even realize these two interpretations clash. And so there are some people who are changing radically their style of physics instruction to try to bring those together. And
So one of the problems that we have here is that is I would call programming in the large. So that I think it's a very different skill to be able to work by yourself than to work in large.
Programming in large is either a large team or a large code base, not frequently taught at the undergraduate level.
We don't even know how to think about it, right?
Well, there's that issue. But, as you said, we could perhaps, just give them experience with it. And even if we didn't know the right answers, maybe that would even be better, though. I mean, it would be at least one step in helping people get up to speed. Yeah, we can help. Yes, Ivan.
I'm just wondering about kind of responding to the question that he raised about how do you actually make the students comfortable in an environment when you're supervising or watching them. And the question for you is, have you looked at tools that can be part of their development environment that will get the data about the compilations, the state of the code that they are working on, all that kind of stuff? And you can actually reuse it both in class and in the lab way.
A graduate student at the University of Maryland, Jamie Spacco, recently defended, and as part of his thesis, he developed a plugin for Eclipse. And so for the past 3 years at the University of Maryland, every student in every programming class, since they all use Eclipse, whenever they hit save, there's been a CVS commit done on their code. And so they have 3 years of every save of every student studying computing at the University of Maryland. And you don't even want to try to look at that data set. It's ugly. But a similar fellow has done a thesis at the University of Kent in Canterbury with a similar development environment they have there. In my particular, I think there is some very interesting data you can get from that. But you do get overwhelmed in data very quickly, especially if you're doing any sort of, because once you've got a tool, you're like, hey, let's have everybody use it. And then you have to try to figure out what is meaningful there. And you can end up with the same quantitative, qualitative problem that we've had before. And Jamie and this other student have both expressed to me that I should be very wary of going there. My particular groups that are working on projects right now aren't going to go the tool building route. One, we don't have the resources to build tools. If there are 5 of us on a project, then we have 5 development environments that are used. Some students use BlueJ, which is a version, I think, of the Eclipse IDE that's developed for students. Some students use Eclipse. Some people are running Windows. Some are having them log into Unix machines. Some people are using VI. Some people are using Notepad. Some people are, typing, Java, C to compile. Some people are using C++. Some people are using something else. And so we just have, as many people as we have as many different development environments. And if we actually desired to come up with a tool to study that, it would take us, we'd never get the research done. So we're going with observation to do that. In the same way that some of your developers don't mind being observed because they're pretty, you know, they want to succeed. We have students like that too. You know, they come from somewhere. And so the students who respond to an advertisement about wanting to be part of a study generally have some pretty big egos, and they can handle it. And in the case when they don't, we just stop and we don't analyze that data. So
the only last comment on that is if they self-select and they are very comfortable,
yes.
maybe they're the wrong kind.
Yes, that's in fact true. Yeah, we definitely have the self-selection problem. You have that with qualitative. We do try to target sometimes. We can look at students' background and try to reach some C students or some students at different levels. But it's a serious issue. It's a serious issue. And so that's where, again, I personally, you know, I'm ready to do a lot of qualitative work. I think the two together tell the best story. Yeah, Andy.
So the discussion you had about the physics students not being able to actually understand what happens when two real cars hit each other as opposed to the equations of two cars hitting each other reminds me of like Jay Leno, where he goes on the streets of Santa Monica and asks these really stupid questions about, like, you know, when was the War of 1812? And I have no idea.
I'm always hoping there's a video camera in your face effect on that one, but anyway.
Yeah, so, you know, obviously, a student graduating in computer science might know how to write a for loop on paper because they've done it like 16,000 times, but they might not know, like, given a certain problem, that they should be writing a for loop. Obviously, by the time they reach industry, or by the time they've been in industry a couple of years, unless they've been fired lots of times, they probably get it at that point. So what do you think are the magic bullets, or if there is one, like what are the actual experiences that happen in industry that connect the dots for these people? Because obviously, like, we are graduating some people that do make it in industry.
Well, right. So I actually think we're not in nearly as bad a scenario as the physics people are. And we could probably make some inappropriate comments about why that would be true. But I think we do provide, we don't just tell our students, you know, my homework problems are not, you know, write a for loop that prints out all the odd numbers from 3 to 33. That might be something we do together in class, or a laboratory assignment, which would build them up. But the problems that we give are, you know, like even in the beginning programming class, you know, is write a class that will represent your playlists in iTunes. Okay, so it is applied, and because we're a very practical and applied field, and I think we do work on that. But then there are the key critical aspects that we don't get anything at, which are often communication, how to talk about your code, how to explain your code. The simple question, what does this code do? I actually was involved in a study I didn't talk about because this came out of the multiple choice question study. People said, we gave our multiple choice questions to some educators, and some of them said things like, these are evil questions. Nobody writes code like that except people designing evil tests, because some of the code was nonsensical. And we would see instructors, as they were hand executing this code, struggling to find sense or meaning in the code. And some of this code was nonsensical. It was there to see if you could, you know, catch trip-ups and things like, you know, starting indexing at 1 or something like that. And so we realized, you know, well, that's something all experts do, is they look at a piece of code, and if you hand a loop to somebody, they'll say, hey, this produces the average of all the elements in the array between index A and B. That's a natural way to describe what a piece of code does. And then our friends looked at each other and we said, do you teach your students that? No, I don't teach my students that. So I've been doing it. I've taught it the last 2 terms, and I have that same question given to students the first term when I didn't teach it at all, the second term where I taught it some, and this term where I knocked down, drag them out every day in class. We did these questions, and I said, the wrong answer is, there's a for loop that starts at 1, and while I is less than blah, do this, and inside the loop, if this. And I said, that's the wrong answer. The correct answer is something that's no more than 2 to 3 sentences, and explains at a higher level and succinctly what it does. And as soon as I get the final statistics on the exams that I've graded, I'll tell you that, yes, they're doing much better. I believe I've got at least 90% of them now who are stating things at a very high level. after 10 weeks of instruction. So I believe you can train them to do it, but we're not necessarily doing it. So that's just one thing that we happen to find out that all experts do the same way. What are the other things that happen in industry that people need to be able to do? How do you get involved in a large code base? How do you find a piece of information? How do you recognize what information you're missing? These are the things we need to find out what we do, what we need people to do, and then we can figure out if there's some common way people tend to do it, and then we'll try to see if we can train them.
So something that's a little like the exercise you had there is take a code that's pretty straightforward and add comments to it. It's sort of required that code have comments at some point. But
we take off points, yeah.
The comments that I see are actually, I would say, wordy and vague, imprecise restatements of exactly what the code does. So a comment might be before a for loop, that this is a for loop that adds the numbers up or something.
Right.
And the for loop describes that far more precisely and insightfully than that comment did.
I personally would find that very interesting, and the question is how much can we convince the community that comments are important? That the community of CS educators. That right now, if you give 10% of your homework grade for having good comments, how critical can we be in that? If bad commenting, as you described, we probably give full points for that. How important is it that we not do that? How do we tell them what good comments are? It's almost hard for them to understand what good comments are or not, but we could work on it, right?
Well, I don't think anybody has a good understanding what good comments are,
right.
And therefore they tend to assume that more is better.
Right. Well, and I think there have been some studies showing that people don't read comments.
Well, especially if they're not
to try to understand code.
Not insightful.
Right. Well, and that could be the reason why. It could be.
If you want to take a variation on comments, could you have them just write asserts to verify that the code hasn't been broken by somebody who's changed it?
Yeah.
That is to work out what are the key invariants that you're supposed to preserve.
Well, actually, along those
Well, how about if
lines,
we teach asserts?
the concept of an invariant was new to a dev lead that I was dealing with. I mean, he had never heard of it.
I'm not sure assert is mentioned one place in the first 270 pages of the first book I used, but we don't require them to know that. It seems poorly placed to be doing it maybe in the first 10 weeks, unless we move to a test-driven development introduction, which would be quite a nice thing to do. But, where does that fit in the curriculum? Why is software engineering an elected class in the ACM curriculum guidelines? Why is software engineering a junior or senior level class? We could go on. But we have to, in some ways, you guys are a moving target. Industry is a moving target in computer science. That's clearly one of our issues. But how can we formalize and stay more closely connected with what it is people really need to do? When do we stop just teaching the same things that we were taught? I'm sorry, hang on. Yeah.
No, I'm just wondering what your strategy is going to be to tackle this industry transition.
I need to see what the data is first. I don't know, because I don't know what it is that we are lacking in teaching them.
No. So I meant in terms of finding out what that is.
Oh, I'm going to follow people around. We'll follow people around and watch them, and then we'll ask them to reflect on skills that they found useful in helping to get their job done, and skills that they had learned before that seemed to help them get their job done. Skills they found new. That wow, I can do this and get this. That's the current plan. Yeah, Andy.
So, presumably, if this results in implications for teaching, presumably some teachers who read 60 and IDICE might actually read this and decide, I think I'm going to do this in my classroom. But 60 and IDICE are about 1,000 to 1,100 people who actually show up at those conferences out of the, let's say it's like at least 10,000 to 20,000 people who are teaching computer science, because most of them are research faculty who don't go to these things. No computer science faculty member, very few that I've ever heard of, have ever been taught how to teach. So in addition to understanding what to teach, then isn't there an education component for the teachers themselves to figure out how to do this properly? Like you said that computer science educators are the ones who have to solve this problem because everybody else doesn't care.
Right. which is why next year at your faculty summit, which I believe is going to be targeting mostly junior faculty, you should have me come in and I'll teach them how to teach computer science. It is important. There's the basic issue of time and where what you're rewarded for in the higher education structure. There's the push for positions like mine. I have the stupid title of lecturer with potential of security employment. On the other hand, I am paid to study education, and because of my interest in it, and I teach all lower division classes. At our institution, very few regular faculty who primarily do research would teach any lower division class. But my faculty are interested in making sure that the students that reach them at the junior level can actually explain to them why their code doesn't work. Rather than just coming in, it doesn't work. So they would like us to train them better in all the things that you want. And I think a number of institutions, especially large research state institutions, are interested in that. We impact a large number of the students. The people at the smaller institutions, who honestly frequently don't come to SIGSI, are very focused around having the students learn, and they apply more resources to it. And I think they can get away, and I was one of them too. You can teach in different ways that allow those sorts of things to be taught. And they're all very, very focused on providing their students with the skills they need to go out into industry. They just don't feel like they have the resources to know what that is. I think if we made significant strides, if I could say 5 years from now, if I could post 5 studies in the way I did today about what people need to know to do to succeed in industry, that there would be huge funding from the National Science Foundation and other people to have dissemination efforts for that work. I would like to think so anyway. And besides, when Microsoft says it's important, it's amazing how many faculty listen. Sometimes. Any other questions people have? Great, well, thank you again. Be sure to stay around.